In this video, we're going to look at power series. Power series is the whole reason why we have studied convergence and divergence of all of those other series. So a power series is given by this definition, where it's a sum from n equals 0 to infinity of a sub n times x minus c to the n. Now, if we take that sum, n equals 0 to infinity of a sub n times x minus c to the n. And if we expand that, so if I plug in 0, I get a sub 0 and then n to the 0, so something to the 0 is 1. Plus, now I plug in 1, a sub 1 times x minus c to the first power. Plus a sub 2 times x minus c to the second power. Plus a sub 3 times x minus c to the third power plus, and you get the idea. Now, this is a polynomial. So the whole point of looking at power series was to take a function and look at it as a polynomial instead of looking at it as its original. So we can take a complicated function. We could take natural log and turn that into a polynomial. We could take cosine and turn that into a polynomial. Polynomials are very easy to integrate. They're very easy to take derivatives of, and they're very easy to approximate, like plug in numbers and figure out what a value would be. And so it's nice to take complicated functions and turn them into polynomials. We won't see this in this class, but where this is very useful in engineering comes in looking at differential equations and more partial differential equations. So the entire reason that 3G networks work and the entire idea of taking in that data and then pushing it back onto your cell phone and kind of interpreting it, if you look at the math behind that, it's solving that kind of wave equation of the wave of pushing that data back to your cell phone all has to do with power series. So these are very powerful and very useful tools. I know they look a little strange right now, but in engineering they do come into play quite a bit, and they are very useful. Okay, so remember that a power series is a polynomial. Power series is a polynomial. It's just with stuff with x squareds and x cubes and everything else. All right, so now some other kind of notation in here. I guess I'm going to look at C first, this whole idea of C. So C is called, it's usually called the center. So we'll call that, I guess we'll call that the center of this. And so on an interval, so also in here, I guess we have R. Let's talk about that. So R is the radius of convergence. So if we were to look at this sum, when would it actually add up to something and not infinity? Because why would we ever want to look at a polynomial that adds to infinity if we're trying to approximate something with it? We wouldn't want to do that. So we want to know what values of x the sum converges for. I'm going to write that down. So what values of x does this sum, does the power series, a sub n times x minus c to the n, what values of x does that power series converge? Because we would never want to look at a power series if it diverges in terms of kind of an engineering standpoint. So these x, the values that x would work for would be on an interval. So x would be somewhere in between the center minus r and the center plus r. So the center plus some radius and the center minus some radius. And how I think of this is just kind of on a number line. So here's all of your x's on a number line, and you have some x that's at the center, and it's going to converge to some number plus r and converge, whoops, that's not very good. It's okay, you get the idea. Minus r. So in between these two, these would be the x's where it would converge, right in there. Those are the x's where it works, where you take the center and you add r, you take the center and you subtract r, and those are all the x's where it converges. All right, so now that we have some of the stuff back, let me tell you how to find this radius and the the center will usually be given in the, will be given in the problem, but how to find the radius of convergence and then how to also find the interval of convergence. I haven't talked about that yet. Let's talk about that. So this guy right here is the interval. It tells you the values of x. Now, one thing that's a little bit hard here, those equal signs are big question marks, and those are things that we actually will have to figure out whether x, it converges when it's equal to that number or not. And I'll talk about that in just a second. All right, so let's talk about finding the radius. So to find the radius of convergence r, we are going to use the ratio test. So if you looked back to the ratio test had this limit as n approaches infinity of a sub n plus 1 all over a sub n. That limit right there, when you take that limit, that is equal to 1 over your radius. So what I'm saying is find the limit, and r is equal to 1 over whatever that limit was. Okay, so that's your radius. That's how to find the radius. Now, the convergence, or the interval. So, interval of convergence. There's 3 different possibilities. So, the first possibility, if your radius is 0, if you draw out that number line, here's x, here's c. If your radius doesn't go anywhere, it only converges when x is equal to c. And that would be your interval. That would be it. The only place it would converge is at c. If the radius is equal to infinity, if you go to the number line and you go to c, and your r is infinity, you're going to go infinity in the positive direction. You're going to go to negative infinity in the other direction. And so the interval of convergence, the power series would always converge. Any x, you could plug in any x, and that power series would sum to a number. The third thing is if you get r equal to some other number. So if r just is a number, then your interval would go from that c minus r to, let me write it out like I did before, from c minus r to c plus r. And there's a very important detail in here, and that's these equals signs. You have to check each endpoint. I'm putting that in red, and I'm underlining it in bold because it's so easy to forget that detail. And it's also fairly lengthy to go through and kind of check each different endpoint. All right, so let's look at some power series and let's figure out some radiuses and intervals of convergence for them. So we're going to find the radius and interval of convergence. And let's look at the sum from n equals 1 to infinity of x to the, let's just do x to the n all over n factorial. All right, so let me just back up just a little bit because we've been looking at power series, right? I wrote out this power series as a sub n times x minus c to the n. So some clarifications as far as kind of what things are in this problem. You have an x minus c to the n here. Here you have an x to the n. And so in our problem here, the center would be 0 because we have just an x to the n. And then in our problem, the a sub n is everything else just with n's in it. So the a sub n is going to be 1 over n factorial. All right. That a sub n is important because when we do the ratio test, we only use the a sub n. So we're going to take the limit as n approaches infinity of, we plug in n plus 1. Sorry, I'm going to actually erase that and make that bigger because I'm going to flip and multiply by the reciprocal. N plus 1 times the reciprocal when I just plug in n. So the n factorial cancels from the top and the bottom, and what I'm left with is just an n plus 1 on the bottom there. And so my limit, I end up with the limit is 0. Now remember that the radius is 1 over that limit. And so essentially the radius in this case is, I'm going to write something so illegal right now. It's 1 over 0, which is infinity. Right, so radius is 1 over that limit. So our radius in this case, radius was infinity. And if the radius is infinity, then the interval, meaning what x's could we plug into this series right here and get a sum? For what x's would that converge? And the answer is any of them. Because the radius is infinite, you can plug in any x. You could try this. You could plug in 2, you could plug in 100, you could plug in any x, use those rules that we just have on that summary of convergence and divergence sheet, and you'll see that it converges. All right, so let's look at another example. Let's look at the sum from n equals 1 to infinity of x to the n all over n times 3 to the n. Now, once again, notice that there's no, well, c is 0 in this case. So c is 0 because of those x to the n's. Using the ratio test on everything that doesn't have x's in it, I plug in n plus 1 and multiply by the reciprocal when I just have n in there. So this would be a limit as n goes to infinity of n 3 to the n in the numerator, and then the denominator, I've got n plus 1 times 3 to the n. I can cancel those 3 to the n's, and now I have the same powers in those n's. And in the numerator I have 1, and the denominator I have 3. So my radius is 1 over that. The radius is 3. So the interval x would be in between c plus 3, which is 3, and c minus 3, which is negative 3. So this was c plus the radius, over here was c minus the radius. And now here is this really important part. I have to check the endpoints. So checking the endpoints, I need to check what happens when x equals negative 3, and then I need to check and see what happens when x is equal to positive 3. All right, when x is equal to negative 3, so I'm taking negative 3 and I'm plugging it back up into that original equation. So I get the sum from n equals 1 to infinity of negative 3 to the n divided by n 3 to the n. I can cancel those 3 to the n's if I factor out a negative 1 to the n. So the 3 to the n's cancel, but I was still left with a negative 1 to the n in the numerator, and then I still have that n in the denominator. So now I look at the sheet and see what test I would use. I have that negative 1 to the n, and it leads me to alternating series. So for alternating series, the 1 over n has to be decreasing. Yep, that's true. It has to be positive. That's true. And the limit as n goes to infinity of 1 over n goes to 0. Yep. And so this one converges. Converges, we just use alternating series. And so because it converges, it will converge at negative 3. So I'm going to put an equal sign right there because the interval would include negative 3 in there. All right, now let's check 3. So I'm going to plug in 3. The sum from n equals 1 to infinity of 3 to the n all over n 3 to the n. So the 3 to the n's cancel. And I'm just left with 1 over n. That's a p series. P is equal to 1. That's not bigger than 1. It diverges. So it diverges by p series. And so that means that that inequality stays. There's no equal sign there. So my interval then goes from negative 3 to 3. So meaning if I plugged in any x in between negative 3 and 3, but not including 3, into that x, and I added everything up there, it would converge. All right, let's do one more example where the center is not. Let's look at the sum from n equals 1 to infinity of n times x minus 4 to the n all over n cubed plus 1. All right, so I am going to ignore everything with x's in it. Here is everything with x's. Everything with x's. This also says that my center is 4. So the center is 4 and the a sub n is everything else in there. Everything else that is not blue that I haven't boxed. All right, so using the ratio test on those a sub n's, I plug in n plus 1 divided by n plus 1 cubed plus 1. And then I'm going to multiply that by the reciprocal, so n cubed plus 1 divided by n. Now, if I multiplied everything through on the top, the biggest thing I would get is an n to the 4th. And what's in front of n to the 4th is just 1. In the bottom, the biggest thing that I get is an n to the 4th, and what's in front of n to the 4th is just 1. So my limit is 1. Now, noticed on the ratio test that usually would mean that you don't get any result from it. You'd have to use a different test. But this is only just giving us our radius. That's it. So we don't have to worry about that. So the radius is then 1 over 1, which is still 1. All right, so our radius is 1. So the interval would then be, whoops, I don't need an equal sign yet. I don't know about that yet. Okay, so the radius starts being the center minus the center plus the radius, sorry, which is 5. And then the center minus the radius would be 3. So 5 came from center minus radius plus radius. And 3 came from the center minus the radius, 4 minus 1. All right, so here's my interval to start. And now I have to check those endpoints again. So I've got to check and see what happens when x is equal to 3. We'll start there. So I plug that into the sum. 1 to infinity of n times 3 minus 4 is negative 1. That is all over n cubed plus 1. I have a negative 1 to the n. And I can see that the limit of n over n cubed plus 1 equals 0. So I'm thinking alternating series, but the n over n cubed plus 1 has to be greater than 0. Yes, it is. And it has to be decreasing. So if I plug in n plus 1 for all the n's, that has to be less than the term before it. Now the n plus 1 is bigger, but in the denominator, I plug in n plus 1 and then cube it. That is something that's way bigger, and so the denominator would then be way bigger and the whole thing would be smaller. You could also multiply and check this. All right, so it's decreasing, it is greater than 0, and the limit's 0, so this one converges, and we used alternating series test. So it converges, so it gets an equal sign. Then we need to check and see what happens when x is equal to 5. So if I plug that in, I've got n. 5 minus 4 is 1, and 1 to the n is 1. Now, when I look at this series and I see that it's polynomial and polynomial, I like to use the limit comparison. Because if I chose 1 over n squared and took a limit as n goes to infinity of n over n cubed plus 1 divided by 1 over n squared. So divided by 1 over n squared is multiplied by n squared over 1. I get 1. I'm looking at limit comparison right now. And if you look at your sheet under limit comparison, that limit, if it's greater than 0, and it is, then either both the series converge or both diverge. So what about this original I looked at? Let's see, p is equal to 2 on that one. That's bigger than 1. That one converges because it's a p series. And so the original will also converge. 1 to infinity of n over n cubed plus 1 converges. We used limit comparison for that one. And because that one converges, it adds an equal sign to that 5. So our interval goes from 3 to 5 and inclusive of 3 and inclusive of 5. All right, so all of this video is just about trying to see exactly the values of x for which a power series will work.